Alright, so now we're going to actually look into some calculus of sequences. So that's going to be pretty cool, I guess. When you think of sequences, we can, let's see, what else can we do with sequences? I keep doing that in, sequences. Sequences and calculus. How do they go together? And that's what we're going to be introducing. So I remember we built derivatives based on limits, and we built integrals based on limits. We can also base sequences and series based on limits. So what if we take a limit? Do a limit, right? What can we do with limits as n approaches something of a of n, right? We can see what happens what happens to the sequence as we go to infinity, possibly, right? That's probably the best thing we can do with sequences and limits right now. So we're going to be focusing on that. How limits and sequences go together. So this is what we're going to be focusing on, that idea. So first off, we have to think of this idea of converging and diverging. So these are two important terms we need to know. Converging means, in terms of calculus and sequences, is basically the limit as n approaches infinity of the sequence a of n is equal to a number. We're going to give it L. L is the number. Diverging is the limit as n approaches infinity of a of n is infinity if it's inconclusive, and we'll see why inconclusive is given as an option. Infinity, negative infinity, inconclusive if it goes on like to a huge number. Converging means that the value that we know, like 1 or 1/2, or maybe like 3, like a physical number that you can, an integer, a real number, not infinity, because infinity is a huge number. That's diverging to infinity, right? So that's what we can use calculus for. So let's actually do a very simple one. Given that a of n is 2n minus 1 over n, this is how they would pose the question to you. Does this converge or diverge? And when they say converge or diverge, you have to think about limits. Think about limits. Limits, so we want to take the limit as n approaches infinity of a of n, which is the same thing as limit n approaches infinity of 2n minus 1 over n. So how would we've done some types of limits like these before. These were pretty simple in limits when we were learning about limits for the first time. We know what the answer is, but I'll just walk you through it. Can you use the same laws as limits? That's the question. And the answer is yes. You can separate them through division, subtraction, multiplication, division. You can do it, take out a constant. You can, do all those stuff that you did with the limit laws before in whatever, the beginning of calculus, right? So what I'll do is I'll do this. N approaches infinity. I'll separate them first. Right? Let me write that better. We know this goes away, so it is 2. This whole thing's 2. This limit evaluates to 2, and then this, if you plug in infinity, goes to 0, right? So the limit overall is 2. So the question is this a convergent sequence or a divergent sequence? Well, since it's actually a physical number L, we're like 2, right? We can say it converges. Let's look at another example. Let's see, what's the, let me go back down here. There we go. So example 2. What I want to look at is, I want to look at this series. So I'm going to find a of n, which is equal to, so this flip-floppy term, right? N minus 1 over n. And then, as always, remember n has to be a positive integer, right? It can never be like halves or like something like that. So think of it like that. So converge or diverge, C or D. I'll just write it as, right? So this one's a more involved problem because it's kind of confusing. But we have a flip-floppy term and then we have a actual function, right? Let's kind of list the terms really quickly. Let's do like a couple, maybe like 5-ish. So a1 is equal to what, -1, and then what is this, 1 minus 1 over 1, which is 0, so it's 0. This converges 0, I mean this is 0. Let's see, a2, this is 1 times, let's see, 2 minus 1 divided by 2, that's 1/2. That's 1/2, right? a3, let's just do 3 terms. Actually, let's do 5. So -1, 3 minus 1 is 2, divided by 3 is 2/3. -2/3, right? This is equal to -2/3. a4, this is 1, now it's 3/4, which is 3/4. Right? It's kind of look like we're 3/4 is closer to 1 than 1/2, kind of we're like getting somewhere, right? If I were to continue this, we'll be approaching something. Well, let's see. So that's why we take the limit. How do you take a limit of this? That's a bit weird. Right? We're kind of, from this point, we're like trying to stay close to the center, right? So it's kind of like if I were to draw it, and this is n, this is the n axis, this is 1, and then we have the vertical axis, which is what a of n is, right? 1 is 0, 1/2 is like probably here, -2/3 is like a little bit bigger than this distance, 3/4 is higher, this is even lower, and this pattern of getting farther apart happens, right? We're getting like bigger here, but it's actually more like this. You see that the values are just flip-flopping right here. If I were to like pretend it kept on going, it would get bigger and bigger, but it would actually be limited by 1. So it's flip-floppy. This is what an example of inconclusive. Inconclusive. Meaning you don't know what the limit is, so it doesn't exist, right? It's going to be flip-flopping from positive to negative. It's not going to, you don't know what the infinite term is. So you don't know if it's going to be here, if it's positive or negative. So this is when we say it diverges. This is an example. And then, let's do our last example to show one that is a, let's do a recursive one. b1 equals 4, oops, and we know the nth term is defined as bn minus 1 plus 2 for n is greater than 2. Not too bad. If we take the limit as n approaches infinity of b of n, we're going to see that we're just going to keep adding 2, right? We're just keep adding 2 every single term, so then it's actually going to tend towards infinity, so we say it diverges automatically. So that's the end of that problem. We can look back at all of these. We did 3 examples, one where it was converging and then finding an inconclusive series where it flip-flops, that's a common example, and then an infinite one. But the main idea is knowing what converging and diverging is. So let's move on to the next topic. The next topic is something that I always found confusing. Maybe you've heard of this before, the sandwich theorem. It works. Same with sequences, same with limits, it works. So here's the definition, and I'll write it here. If, let me zoom in closer, hopefully if I can, there we go. If the limit as n approaches infinity of a of n equals the limit of this of c of n, which is equal to a number, right? It doesn't diverge. And there's such a thing that where this happens, right? For all n that's greater than an integer that we want, right? Then we can say that the limit also is the same as the other two. So it's kind of like sandwiching it together, because we know this is between these two numbers. Let's say we don't know for sure what this is, but we know these two and it's between these. If they're the same number, we're just sandwiching b in between a and c. So that means it should be the same thing. Here is the example for this, and then I'll introduce one more thing. So this is example 4, I believe. So I'll give you this sequence: cosine of n over n. So this is our a of n. Does it diverge or converge? D or C? So we have to be using the sandwich theorem, and that's kind of weird. What do we know about cosine? We know cosine of n always has to be between these two numbers. This is always usually what we like to start with, between two numbers that we know for sure. It takes on values between these two. What happens when we divide it by n? All sides by n get divided. And then we can take the limit as n approaches infinity of each term. Oops, I forgot the limit here. And then same thing here. Limit n approaches infinity of 1 over n. So what? What does this evaluate to? This evaluates to 0. We don't know this one. This is what we're trying to find. And then this is 0. That's kind of an interesting result, right? We have 0. This has to be between 0 and 0. By the sandwich theorem, it should be 0, right? So therefore, this is the therefore symbol. The limit as n approaches this is 0 via the sandwich theorem. Or squeeze theorem, whatever you learned. And it converges as a result, right? That means it converges. Oops, did not mean to bring that over. The last topic is a theorem, and that's very weird. A theorem that's super important when we talk about that is called the Absolute Value Theorem. And this absolute value theorem, we have to look at this sequence. I keep saying series. If the limit as n approaches infinity of the absolute value of the sequence is 0, then the limit as n approaches infinity of the sequence itself is just 0. So remember when I was talking about that flip-floppy term? Let's look at that example really quickly. Let's look at a very similar one actually. So let's do this, and then let's do this. Let's do, what should we do? That's a good example. Let's look at this. Let's do this. I'm going to add the squared term on the bottom, just for the purpose of the example. We see that if we take the absolute value, this thing doesn't matter anymore, right? Take the absolute value, this thing doesn't matter anymore. We're just taking the absolute value of this. And we take the limit as n approaches infinity of this now. And this approaches 0. That means we can be for sure saying that the a of n, as you take the limit, it goes to 0 as well. This is a theorem, and it's super important, especially when we talk about series. So that's it for sequences, and we'll be talking about series next time actually. So